Hey everyone, so we're always hearing that cement is this massive source of carbon emissions, right? But what does that actually mean? Where do those emissions really come from? Well, today we're going to figure that out. We're going to build that final carbon footprint number from the ground up, piece by piece, so you can see exactly what makes this stuff so tricky to decarbonize.
So here's how we're going to do it. First, we'll look at the emissions that are literally, and I mean literally, baked into the rock itself. Then we'll talk about the insane amount of heat you need and the fuel you burn to make it all happen. After that, we'll see how the stuff you actually buy isn't pure and how that changes the math. And finally, we'll layer on the real-world stuff like electricity to get our final all-in number.
You hear this phrase all the time, hard to abate. It's a great buzzword, but what are we really talking about? It means that a giant chunk of the emissions has nothing to do with burning fossil fuels for energy. Nope, it comes from a fundamental chemical reaction that you just can't get around. Let's dig into that.
Okay, so our story starts not in a factory smokestack, but with the rock itself, limestone. This is where the whole carbon problem with cement really begins.
The critical process here is something called calcination. Now, it sounds super scientific, but the idea is actually pretty simple. You take limestone, you heat it up like crazy, and it chemically splits apart. One part is the lime, which is what you want for cement, and the other part, pure CO2.
And here's what that looks like as an equation. This right here is the heart of the whole issue. You've got limestone, CaCO3, you add heat, and it breaks down into lime, CaO, and carbon dioxide, CO2. See, the CO2 isn't just a byproduct of burning fuel, it's a product of the rock itself. There's no way to make the lime without releasing the CO2.
And this is where the math really blows your mind. If you just look at the chemistry, at the weights of the atoms, for every 100 pounds of limestone you cook, you are chemically guaranteed, it's a law of physics, to create 44 pounds of carbon dioxide. It's a fixed ratio. You can't change it.
So what does that mean for us? Well, the key ingredient in cement is called clinker, and it's about 65% lime. When you run the numbers, you get this. For every single ton of clinker you produce, you are going to release 0.52 tons of CO2, period. It doesn't matter how you heat it. This is our foundational, unavoidable emission.
But of course, limestone doesn't just decide to break down on its own. You have to get it incredibly hot. We're talking furnace-level hot, and that takes a huge amount of energy. So let's ask the next question. Where does that heat and all its emissions come from?
All right, on to part two. Let's add that next layer of emissions, the fuel we're burning to heat up that giant kiln. And you're about to see, what you burn makes a really big difference to our running total.
We're going to compare two of the most common fuels. First up, coal. A coal kiln is actually surprisingly efficient because the coal particles themselves glow red hot and they radiate heat really well. Natural gas, on the other hand, burns with a clear flame and produces a lot of steam, and that steam basically just carries a bunch of your precious heat right up and out the stack, which makes it less efficient.
So let's run the numbers for a coal kiln. You need to get about 3.5 gigajoules of heat into the rock. But your burner is only 80% efficient, so you actually end up burning enough coal to generate almost 4.4 gigajoules. This all means you're adding another 0.40 tons of CO2 to our tally for every ton of clinker. Okay, now for natural gas. Remember, it's less efficient, so to get that same 3.5 gigajoules into the rock, you have to generate even more total heat, a full 5 gigajoules. But here's the twist. Natural gas is a cleaner fuel for the same amount of energy. So even though you're burning more energy, the CO2 is actually lower, coming in at about 0.28 tons.
So let's see where that puts us. Here are our new totals. If you take our unavoidable rock emissions and add the fuel, you can see that 1 ton of clinker from a coal plant now sits at 0.92 tons of CO2. And for a natural gas plant, it's a little better, at 0.80 tons.
But hang on, we're not quite done. We've been calculating the emissions for clinker, that super important binding ingredient. But the bags of cement you go out and buy aren't actually 100% clinker.
If you grab a standard bag of what we call Portland cement, it's really only about 85% clinker. That other 15% is a mix of other materials, like gypsum or fly ash, that get ground up and blended in. Now this is actually some good news for our carbon number, because we're basically watering down the most carbon-intensive part. The emissions for each ton of the final product go down. We just take our kiln totals and multiply them by 85%. That brings the coal plant number down to 0.78 tons and the natural gas plant number down to 0.68 tons.
We are so close to the final number. There's just one last thing we need to account for. The electricity. I mean, you have to run all that heavy machinery for crushing and grinding, and that power has to come from somewhere, right? These are our indirect emissions. Think about it. You're taking giant boulders of limestone and these super hard clinker nodules and crushing them into a fine powder. That is seriously energy-intensive work. On average, it takes about 110 kilowatt-hours of electricity to produce 1 ton of cement.
Now, the carbon footprint of that electricity really depends on the local power grid. So for our example, let's use the grid in Alberta. With what's called an emissions factor of 0.55 kilograms of CO2 for every kilowatt hour, that electricity adds a final 0.06 tons of CO2 to our total for every ton of cement.
And there you have it. This is our complete, real-world carbon footprint for a ton of cement made in Alberta. It's about 0.84 tons for a coal-fired plant and 0.74 tons for a natural gas plant. And you can see it all stacked up, the big base from the rock itself, the middle chunk from the fuel, and that little sliver on top from the electricity.
But here is the most important takeaway of all. Just look at those final numbers. Even in the best-case scenario with cleaner natural gas, that huge chunk at the bottom, our unavoidable process emission, still makes up over 60% of the entire footprint. You can't just switch fuels and solve this problem.
And that really leaves us with the big, tough question. This is what people mean when they say cement is hard to abate. When the pollution is literally locked into the chemistry of the material you need, how do you ever get to zero? Decarbonizing the very foundations of our modern world is going to be one of the biggest challenges we face.